All right, hi everyone. We're going to start with the guest lecture today by Jingyu Song. He's a PhD candidate in the field robotics group, and today he's going to talk to us about his research in localization and mapping with cameras and acoustic sensors for unmanned vehicles. So give him a warm welcome, please.
So, hello everyone. Very excited to introduce my research about marine autonomy and mostly focusing on localization and mapping for underwater robots in challenging environments. And also thanks Katie for inviting me. And so the two projects I'll be introducing today have a lot of overlapping points with I think the ROB572 course. So hopefully this presentation can provide you with some like a raw picture of how you can relate the course materials and to build your own research based on this course. So before we go to the two projects I'll be talking about, I just want to give a brief introduction about myself. I did my and I did my master's here in the ECE program with a track in robotics. That's where I kind of built my knowledge and skills in robotics. And now I'm a PhD candidate working field robotics group and also for Center for Autonomous Vehicles. My research interests are mainly twofold. I work on perception for both autonomous underwater robots and also autonomous vehicles, and mostly using radars for sensor fusion. But today I'll be mostly talking about this localization and mapping in the challenging underwater environments. So feel free to interrupt if you have any questions. And I think there isn't like too much need to motivate people sitting in this room about like why marine autonomy is important. But I just want to show like two examples that underwater unmanned vehicles can like help with environment monitoring and also like shipwreck survey. Some benefits like safety, cost efficiency make achieving a marine autonomy very important. And this is a figure from a paper called The Grand Challenges of Science Robotics, which is a flagship journal in robotics, and the papers or research works published there are usually like well recognized by the community. And in this paper, it has a lot of coverage of like talking about how important and challenging that achieving autonomy, especially like navigation and exploration in those like challenging environments, including like underwater environments. And from this figure, we can also see some example challenges such as like the featureless environments, the low light condition, and also the environment disturbance such as wave and current can also like pose challenges to localization and mapping. So the first project I'm going to talk about specifically focus on uncertainty aware localization and mapping. This is a like general like ROB robot that we built in our lab. It has like sensors such as cameras, DVO, Doppler velocity log, and like a 360 sonar and also pin sonar. It also has a barometer for depth measurement and also IMU for measuring angular velocity and acceleration. So it's not for like a general robot on land. Camera is usually like a very important navigation sensor, and a lot of localization methods for like robots on land can usually like work very well with camera only. However, in underwater environments, no matter it's like forward facing or downward facing, cameras are usually not like as good as a navigation source or like as the only navigation source. For example, I put a picture here. The first one is a forward-facing camera, and you can see that actually when the robot moves forward, the repetitive structure pattern would just like cause all the visual odometry not working properly. And this is a downward facing image, and as you can see, it's very low texture, and all the no matter it's like indirect like feature-based visual odometry or direct visual odometry would just not work to solve any relative transformation here. So in this project, we actually mainly focus on achieving uncertainty aware localization and mapping based on the acoustic sensors. So overall, among those sensors, we will be using DVL parameter and IMU for localization, and for mapping, we'll be using the acoustic range measurements from the DVL and the 1D pin sonar for this project. So when we talk about uncertainty aware, one question is what is the uncertainty and what type of uncertainty we want to hear about. So here is a video that we run the wave generator in the MHO in Central Campus. And the first question that this project seeks to answer is that can we trust the DVL at the same level as in the calm water? Because DVL is an acoustic sensor and it is also very important for underwater navigation as it provides direct linear velocity measurement. So this is the first question we want to answer. And the second question is that for a typical filter-based localization method, if there is no direct measurement, for example here, when we plot this common filter output for the position, we can see that there is an increasing pose uncertainty in the x and the y axis because there just isn't a direct measurement on this axis. So the nature of the common filter will just like keep increasing this pose uncertainty. So our second question is that can we trust the estimated pose and use that for mapping similarly from the beginning to the end? So overview of this project, the goal is to just design a localization or state estimation and mapping system that can account for environmental disturbance and also pose uncertainty. In this project, we seek to answer 4 questions. And first one, how do we actually know if environmental disturbance is in fact influencing the sensor measurement? The second one is that if there is such a environmental disturbance, how can we like measure and also quantify this influence? And once we have this quantified influence, how do we incorporate or integrate this in our localization or state estimation algorithm? And the fourth question is how to effectively propagate the pose uncertainty to mapping so generation map is aware of this increasing pose uncertainty. So let's start with the first question. When we want to find the environmental disturbance that influences the sensor measurements, our direct thought would be just like, okay, we have this sensor measurements. Can we just get the ground truth measurements and just compare them, and we'll be able to know if this environment disturbance actually affects our sensor measurements. Here's a recap that the DVL measures the linear velocity. So as a result, we want to have this ground truth velocity. But the challenge is that for underwater robotics, just getting ground truth is like fundamentally hard question. This is a structure from some typical methods we use structure from motion, such as CoMap, to solve this poses offline to serve as a ground truth. There are also like underwater motion capture systems that can provide you with like ground truth pose tracking. But for when we were doing this project, our challenge would be the CoMap would just fail with our collected big data because there just isn't enough visual features that can be solved, and we don't have an on-site mocap system. So we have to be creative about how we design this experiment. So our solution is to rigidly fix this robot to a movable carriage in the water tank in the Central Campus MHO, and they have a carriage that can move just along the X direction, and they have some sort of ground truth reference position for the carriage position, so that can be serving as our ground truth position for the robot because we are rigidly fixed that and we know this ground truth transformation. This is a robot we built in our lab, and we equip it with DVL and 1D pin sonar, they are all looking downwards so that they can provide us with sparse range measurements of the bottom surface. The IMU and the parameter is also are also equipping this electronic enclosure in the Blue RV robot. We run an experiment where we keep this carriage static and just run the waves. Here is a video. And we run the wave generator in the MHO and just manually introduce this wave disturbance in the system, and we record all the sensor measurements. So in this experiment, because the robot is rigidly mounted to this static carriage, so actually the ground truth measurement for like DVL would be just like 0. But we still record a very minor fluctuation in the DVL velocity, which is here. So we record all the data and run like an offline data analysis to get the empirical mean and the variance based on our static experiments with different wave amplitudes and wave frequencies. So this is our way of quantify this, how the wave disturbance can cause the sensor measurements to be inaccurate. But once we have this quantified disturbance factors, our question would become like, how do we integrate this disturbance in our localization design? So before we go to the third question, I just want to give a brief introduction about state estimation and common filter, because that's what we use for estimate the robot pose. So state estimation is in general a problem that tries to estimate the state given observation and measurement. There are usually 2 steps in like general state estimation algorithm. First one is prediction step. That is, given this control input and your previous state, how what is the predicted state of the current step? And the second step is a correction step. That is, given this predicted step and also the sensor measurements, how do we correct our state so that it aligns better with our sensor measurements? So this is a general framework for an extended framework, common filter framework. And among them, the third step is usually called innovation step, and that is basically to calculate this error from your from your sensor measurement and also your estimated sensor measurement from the sensor model you have. So the sensor model here is a given predicted state, what the measurement should be looking like. So we integrate this characterized environment disturbance as an additive noise in our sensor model, so that so as a result, our sensor models will be aware of this disturbance when there are waves on the DVL measurements, and when it calculates the update to correct the predicted state, it will be more cautious when we have like a larger noise or larger disturbance on the system. And as a result, our proposed method is able to outperform the baseline unscented common filter, which is a standard common variant of common filter. And we're also able to, the second one, the picture on the right is a trajectory comparison where we can see that our proposed method has the least amount of drift and aligns with the ground truth the best. This is our ablation study where we break down the improvement based on our 2 main contributions. We have we accommodate this environment disturbance by including an added noise in the sensor models and also adding a global calibration of our DVL measured orientation. So collectively, they were able to give us the best performance. And when we have this enhanced localization method, the problem of increasing post uncertainty is still unresolved, and also so that we want to find a way that how to effectively propagate this increasing post uncertainty to the mapping. The last question we want to address is that, but before we go to the last question, I want to just introduce a common mapping representation known as occupancy grid mapping. So in this mapping framework, the environment is represented as by a grid, and here is a 2D example where we just discretize this 2D space, and for each cell, it will be either free or occupied. And in common practice, we will usually use a binary random variable to model the occupancy. So when this variable is when its value goes to 1, it means that it's more likely to be occupied, and otherwise, when it goes to 0, it means it's more likely to be a free space cell. And in our framework, because our robot operates in the 3D space, so we just extend this to use 3D occupancy grid mapping. And the map is actually a function of just like a function that returns you the occupancy of each map cell. And among those 3D occupancy grid mapping methods, a recent like state-of-the-art method is using like a kernel to describe mapping point measurement and their spatial consistency in nearby cells. So, for example, here with our robot and its estimated pose P, and if we have a range measurement, so of a point in the space, the kernel describes the spatial consistency of this measured point in nearby cells. So intuitively, it shows that when a cell is closer to this map point, it will have like higher kernel value. So that means that this cell will be more likely to be occupied. And for cells that is like a bit far away from this map point, it will just like have a lower kernel value. So we found that for like a standard kernel function, there are 2 parameters that we can play around, and that is a very nice place where we can integrate this increasing post uncertainty. The first parameter is the kernel length. So as you can see, when we increase this kernel length, the kernel will be less centered, so that it means that similarly a map point here with a larger kernel length, it will be affecting like a larger area, but with a less centered value. And another parameter is called signal strength, and it basically just like controls the height of this kernel. So that is also effective when we want to like specify different confidence on our mapping or on our like range measurements from different sensors. So we add this adaptive kernel so that we vary this kernel parameters based on the post uncertainty. And in fact, when the post uncertainty increases, we increase this kernel length so that a larger area is updated by a range measurement, but with a less centered kernel function. And our improvement also includes with decomposing this kernel. So instead of having like a combined 3D kernel that searches neighboring cells in the 3D space, we decompose it in like X, Y, and Z axis separately. The reason is that when we mentioned this increasing post uncertainty, we actually have, our method can actually maintain a constantly low uncertainty for the Z-axis, because for underwater robots, we have a parameter or known as a pressure sensor. There is a direct measurement on the depths on the Z-axis. And this is the depth measurement or the pressure sensor measurement is really very accurate. So that helps to maintain a very low uncertainty on the z-axis. So as a result, we decompose this 3D kernel. So and for the x and y axis, where they have this constantly increasing uncertainty, our method is able to vary this kernel, but we remain very strict on the z-axis because that is where we have this precise measurement on the pose. So this improvement is actually fine-tune this kernel-based method for underwater robot because this is where we usually have this direct depth measurement. As a result, we can see here for a standard kernel that searches neighboring cells, for a range measurement, a larger area would be affected and mapped, but they are usually, but that 3D kernel would involve the z-axis, but our method would be more accurate, and for like for the same range measurement, our method would maintain more accurate against the ground truth. To evaluate our map, we capture a 3D scan of the environment. We collect the data and we show the map that overlay with this 3D scan. And the quantitative results also show that with the adaptive kernel design and our proposed localization method, we are able to maintain the lowest mapping error across all the baselines. This is another qualitative example where we show that in the MSO there is slightly immediate change in the altitude, but our method is still able to capture this this change in the map, and we are also able to, and our method also has this informative representation about the uncertainty of the reconstructed map. As we can see, the boundary between the occupied space and the free space has higher uncertainty, and that's very informative for the downstream tasks such as path planning. Yeah. So a quick summary of this, the first project I'm talking about. We designed real-world experiments to characterize the wave disturbance on acoustic sensors. We also integrate the effect of disturbance into a probabilistic framework for localization and mapping. And we extend an existing mapping framework to be capable of propagating pose uncertainty with an adaptive kernel. But there is still some limitations with this method, and that's why we are extending it, and that's why we'll be talking about our second project. The first limitation is that the acoustic sensor measurements are still sparse, so that the generated sparse maps are not as informative as a denser map, which is usually preferred by navigation. And also, here is the example that with a straight line log, the generated map would be just very sparse, and from the DVO range measurements and the in-sonar measurements. But for any map that's generated from like a camera or like a RGB camera or RGBD camera, you'll be very dense, and it contains important information for effective and safe navigation. And that's usually preferred because it also provides us a lot of information about the environment. The second limitation is that we are using like a filter-based state estimation. It's not bad, but nowadays a lot of methods are actually using like post-graph-based smoothing methods, and it is more unified because it represents the localization problem as a post-graph, so that it will be very easy to extend to other modalities. As long as you have a corresponding factors, you can just like link your post to different factors, and you'd be just like and solving this would be just like a standard optimization problem. And a key difference between like filtering and the smoothing method would be smoothing is based on all the measurements we have up to now. It can go through all the history in the like interesting time horizon. So it can like modify the history, but filtering, it only cares about the current state. So our second project specifically tries to realize the real-time localization and dense mapping. And our project specifically focusing on realizing real-time localization and dense mapping in low texture underwater environments. We also want to build the overall solution based on a low-cost platform, so you provide better accessibility and scalability. In the low texture environments, visual sensors are usually unreliable as a navigation source. Here are two examples of typical underwater environments where the visual sensors will just provide you with like unuseful or like unreliable information about navigation. But when we talk about dense mapping, then camera, it would probably be the cheapest sensor we can use to construct a denser map, especially for underwater robots. Here is an example I found. That is a recent product of image sonar, which is a like acoustic sensors that can give you some dense reconstruction of the scene. And it is advertised as a high performance multi-beam image sonar at a game-changing price point. And the price is like 9K. So that is probably like the equivalent price for as our robot and with all the sensors on board. So our problem become like the camera is not reliable as a localization source, but it can be very useful for to construct a dense map. Here is like a product that is very popular, like a stereo camera. And you can see the construct, like its depth estimation would be like very dense and has like a lot of important features such as like RGB and also like a depth. So it can construct the scene in very fine detail. And the price for this camera would be just like $499, and that's like an affordable price for us to integrate on our robot. So our overview of this project, we developed a hardware system of a low-cost robot platform with multiple sensors. We also developed a post-graph-based status emission package with customized factors for the DVO and the parameters. And it has robust performance against wave disturbance and also in the low texture environments. We developed this mapping and localization framework based on roles, and it can run real time on an NVIDIA Jetson Orin Nano embedded computer. So just briefly mention about our hardware design. A fundamental challenge to robotics underwater is that you have to make it waterproof. It's not as easy as when we want to add the stereo camera to an autonomous vehicle, we just mount it and it starts working. So for our sensors, such as the camera, the IMU, and the embedded computer, we design a sensor enclosure with a provider called Sexton, and we reserve subcon terminals so that we can like connect the sensor enclosure to the main electronics enclosure of the Blue RV. So all the sensors, all the measurements are synced. This is an overview of our second generation of the robot. We upgraded our robot with additional thrusters to accommodate larger space for our sensor enclosure, and we still integrate the DVO and the pin sonar to look downward. We conduct our experiment in the towing tank at the University of Iowa, and that's where they have the motion capture system. So we were able to obtain the ground truth pose for evaluating our our solution. It also has an artificial beach, so that is very helpful for us to launch a robot, and that is also a good source of evaluating our method to test if we can like map this distance change of altitude, and also test our methods if our method can extend to other vehicles such as like amphibious vehicles. It is also a good experimental site because a typical environment of the bottom surface would be very low texture, and it would be just like very hard for like a person to tell the relative transformation, so that all the like visual odometry method would just like not work with the data collected here. And you also have a wave generator, so we can still generate the waves and test our methods robustness against the waves. Before we go to the like methodology and results, a very important process to use like optic sensors for underwater is underwater calibration. And in fact, calibration is not as easy as it sounds like. Like it's not like a one hour effort where you just like run your software and just like move the calibration board around and you will get a good calibration. There are various packages online. Some popular packages include like Calibre and also MATLAB, and OpenCV also have like support for calibration. There are a lot of calibration targets such as like April grid or checkerboard. And I did have a lot of struggle with getting a good underwater calibration. And when I was like very struggling and very upset about this, I was also attending the IROS conference and got this advertisement handout from a company that specialized just doing this. So if you and your team are struggling with sensor calibration, you are not alone. So that calibration can take a lot of trials and times. And based on our experience, using Calibre and the April grid gives us the best, like the most reliable calibration parameters. Additionally, calibration is not easy underwater. Here's a fun video. That's where we try to obtain some like logs for evaluating our calibration, and I was just like dragged by the robot into the 3-meter water tank. So that is not fun, and also that's like the challenges we have for underwater. But the reward is nice, and calibration is also very important, especially for this project, because with a good calibration, we have a good depth measurement, and it can directly affect our reconstruction or mapping quality. We use this artificial rock to do a qualitative comparison of the default calibration from the stereo camera we have and the recalibration we have completed for underwater, and it was able to reconstruct this to estimate the depths of the rock and the bottom surface correctly. So here is an overview of this method we developed. First, we have this customized low-cost robot platform with multiple sensors. We design a localization stack where we use DVO, IMU, and parameters for localization. We use the estimated pose and the depth measurements from the Z-Mini stereo camera to do a dense volumetric map with an open source package called VoxBox. We developed this full framework in ROS so that to stream all the sensor measurements and run those packages. In our localization stack, we frame this state estimation problem as a fused odometry, and we use GTSM to build the pose graph. In general, our parameters provides us measurements about the depth of the robot. IMU gives us angular velocity measurement and also the acceleration measurement. The DVO provides us with a linear velocity measurement. And in our method, we develop our customized DVO factors and the parameter factors, so it computes the error of the estimated state and the actual measurements, and sends everything into the GT7 to do post-graph optimization. We directly compute the residual or error of the parameters just by like checking the estimated depths against the measured depths. For DVO, we integrate along a specific time horizon to get the relative translation change, and we add these factors to constrain the relative keyframes of the translation. Because we're using multiple sensors, and in general, sensors are not usually perfectly synced. And in our method, our IMU runs at 250 Hertz, and our DVO can run from like 4 to 10 Hertz, depending on the altitude from the DVO to the bottom surface. Our parameters run constantly at 5 Hertz. So we have to deal with this unsynced and varying rate of measurements. And in our method, we decide to use to add the keyframes based on the parameters measurements. The direct benefit is that we have the accurate depths from the parameters for every keyframe. But the question is, at each keyframe, there isn't a synced DVO measurements, and the time gap between the latest DVO measurements and the current keyframe cannot be ignored, because it can be a pretty long time horizon. It can affect the localization performance, especially when the DVO is not like it is having an alternating rate. So we propagate the DVO velocities based on the latest DVO measurement and the IMU measurement, because IMU measures the acceleration. So we are able to propagate the DVO velocity by adding a pseudo propagated DVO velocity into the DVO sensor measurement stream. And then that is able to give us improved performance on the localization. Our mapping method is just directly use the estimated posts and publish them as a rows TF. And we run the workflows to subscribe to the rows TF from our proposed localization package, and also the depth point cloud from the Z-Mini camera. Yeah. Oh,
sorry. I was just curious. So are you, in that process, are you basically like integrating your IMU's acceleration data and then comparing it to the data from the DVL?
No, actually so in the GT7, there is like a pre-integrated IMU measurements where when you have the IMU measurement, you just input that in the IMU pre-integration. And we are able to, so for the latest DVL measurement, we just like, each time we add this keyframe, we just use that IMU pre-integration to propagate from the latest DVL measurement timestamp and get this like newly propagated DVL.
So you're not like comparing the error between your IMU data and your DVL, like?
No, because as that exact timestamp, there is no like DVL measurement as that keyframe.
But the pre-integration is running at rate with the IMU.
Yeah, and that is like accessible by the like a DVL thread, so we can still like query that those like IMU measurements and run this pre-integration. Any questions? Okay. So before we talk about our experience here, I want to show some like state-of-the-art vision-based methods. And for example, OP-SAM3, that is probably one of the most widely used SLAM method, but it struggles with like detecting features in a lot of like periods in our logs, because there just isn't like enough features for it. For another underwater SLAM, like SOTA SLAM method called Aspen2, it can struggle with like initialization, because there isn't like enough like ideal like expected number of features you have, so it has bad initialization that leads to like just like exploding trajectory. Here's a video I run our method, I run ROB572 on our data, and as we can see, when there are like good, not good, but just like a bit more number of features, ROB572 is able to kind of starting to give you estimated trajectory, and that kind of aligns with our eye visual odometry. But when it goes to a region where there is like a less number of features, the ROB572 trajectory was starting to diverge like this. And here's another example I want to show, just try to localize the robot with your eye on the like bottom left video stream. Yeah, that just gives us like a overall picture of how hard that is to use like vision-based methods.
Is that light like shooting through the waves on the bottom or
I
what?
think it's like reflections on the surface and also the light, so you will see those like spectrum. Yeah. That is not like I guess like a reliable features for that can be extracted by the ROB5 and
The caustic effects from the lights and the wave surface.
so hopefully that gives you like some motivations that on the and also understanding like why we are not using visions to do localization. In our like experience, we generally evaluate our method on 2 logs. The first log we run our robot as like a survey pattern of the tank to try to collect enough images to reconstruct the bottom surface. That is as long as like 7 minutes. The second log we run the wave generator to create like wave disturbance, and we drive like 2 squares of in the water tank. In the polling tank at University of Iowa, we only have very like a limited region where we have like valid tracking by the motion capture system. So that is like a smaller area than the overall tank where we can do the localization evaluation. Our method is able to outperform the baselines. The first baseline is a DVL odometry that is directly operated by the DVL sensor drivers, and a lot of methods actually use that to serve as like estimated state. And the second method is a standard like unscented common filter that is discussed in the first project. And our method is able to outperform them by like notably. And here is a qualitative comparison where we can see that when our method like from the starting point to the end, our method can like align the motion capture system trajectory best and has the least amount of drift. So the overall trajectory starts from here and it goes like multiple survey patterns and it returns here, and that's where we can see that our method still aligns with the mocap pretty accurately. Yeah.
I was just curious, do those numbers in the table represent like your errors between your like desired value and your?
Oh yeah, our desired value is a motion capture trajectory, and this those values
The log values, yeah.
is like absolute translation error and absolute rotation error.
Why was the rotation error generally like bigger than the position? There's like a reason for that, or?
The rotation error is like in a unit of degrees.
Oh.
So they were just like different
Okay.
units. So yeah. We also conduct an ablation study, and when we add this pseudo velocity measurement propagated from the IMU, the method you'll be able to outperform a baseline method without this like pseudo velocity addition. The sensor uncertainty refers to like using the DVL measurement uncertainty that is reported from the driver instead of when and compared to like using like constant noise that is like that was done by like previous methods. So with these two key contributions, our method is able to maintain the lowest quantitative error in both logs. Here is a live demo of the localization and mapping package. This is speed up by I think 2 times, and as you can see, this is the first log where we don't have the wave, and the robot is maintained at a medium depth, and our robot, and we show like a video capturing the robot movement in the tank, and the forward-facing camera and the downward-facing camera on the side. This is a pretty long video, and the main idea is that our method is able to maintain pretty accurate, as you can try to do this like localization by yourself and try to just like compare what you get with what is shown here.
So when that changes, like when the black of the Hawkeye changes to blue, that's like the auto contrast of the camera kicking in.
It also I think it's also like at different places the light varies a little bit different, but it has like auto contrast. Yeah. So I think
are you not using the forward facing camera to like map out the floor here?
Yeah, the forward facing camera here is a monocular camera, and obtaining depth from that is like it's not like easy to achieve. And in this method, we are not using forward facing camera for navigation or mapping. We are just like using that for us to when we like when we're just like driving the robot, and also provides us with a little bit more information about what the robot is doing right now. And the second demo is from log 2. That's where we maintain the robot as close to the surface and run the waves. When the robot is close to the surface, it has a large amount of like wave disturbance. So that's why, and that's the reason that we want to like challenge the proposed solution and to see if it is robust enough against the waves. And both logs starts from the beach area, and so that's why you can see this. The beach is also mapped accurately in the map, and you can see this like jumping of the robot localization here that is caused by the wave. And as you can see, the rock is also mapped in the log here, and that is like an object, like a small object we add to the experience sites just to test our method to map the small objects. So here is like a result of the map generated from both logs. In log 1, that is like a survey log, so we can see that it maps the like a bird shape logo pretty accurately, and it aligns well with like the image we captured here. And we have like prior knowledge that the bottom surface is just like flat, so we have this ground truth reference of the bottom surface map and how they should look like, and our method is also able to map the artificial beach, so that which is very important for navigation, because you don't want your like robot to like collide into the beach and also for amphibious vehicles, that is very important to switch between like land and sea mode. In the second log, we show like a heat map of the distance to the bottom surface so that you can see even with wave disturbance, our method is still able to maintain like accurate flat surface in the map. And here is a like qualitative like comparison of the small like rock dimensions we measure from both maps and what we measure on land, and they were pretty aligned. And quantitatively, when using our proposed localization method, the overall solution maintains the best mapping performance. But there are still something left, and I'm hoping that could. I would just like to talk about some future work we have in mind also working right now. So in this work, it's different from the first project I was talking about. Only camera depth measurements are used for mapping. So for camera depth, although it's like dense, but it has range up to like 10 meters. But for like acoustic measurements, although they are sparse, but you can have like a range up to like 100 meters. So we are thinking of fusing these two types of like sparse and dense measurements. So our sparse measurements can help to build like a rough prior knowledge of the environment, while our dense camera measurements can map the environment in more details. And in this work, we specifically focus on low texture environments where visual navigation is just unreliable. But in real world, a lot of things are like mixed with low texture and high texture environments. So in high texture environments, visual navigation is really reliable and can give us like direct like relative transformation that we can add into the postgraph. So an extra benefit we have here is that our postgraph allows natural extension of adding visual factors such as visual odometry of relative transformation and loop closure so that it can correct the drift over time. Another future work we are having in mind is that how to actively estimate the environment disturbance. In the first project, it's like, I guess it's more like a pioneering work that we just like estimate this environment disturbance and assume we have this knowledge, but in more like realistic real world environment, we don't have this prior knowledge, but we should be able to estimate this environment disturbance based on like our visual input, the parameters, like our depth measurement, the ambient capture, angular velocity or acceleration, and also the existing map we have built over time. And can we design a multimodal disturbance estimator and apply that to our existing framework? Yeah, and last, I would like to also thank my contributors, my collaborators, and a lot of those like underwater real world experience require like a lot of people's efforts to like work together, and I'm very lucky to have my collaborators and to make this come true. Yeah. And thank you.
Did you guys look at like the disturbance profile versus depth? Because like, how quickly does the wave effect fall off the deeper that you get under the surface?
I think we run our wave set at 1 Hertz. So I think that 1 Hertz goes to like at a steady point when you measure this wave spectrum, it will be like 1 Hertz. So, and we don't actually have a way to, I guess, to measure this wave on our measurements, but I think all our evaluation is done using the motion capture system, and it has like a fixed reference coordinate, and that is not affected by the wave.
At least the initial experiments we did in MHL, it was like half a meter to a meter for the 1 hertz waves.
I'd also like to point out, as a native Iowan, the phrase bird-shaped logo was very offensive.
Yeah, we spent like 2 times to go trips in Iowa, and every time it's like,
We'll update it to the proper logo.
So part one, you kind of lay out your UKF stuff.
Yeah.
So UKFs are extremely finicky, if you don't have a good observation function. I'm curious as to what exactly your observation function was. I'm trying to piece together what it could be in my head, and I couldn't quite ascertain that from your presentation.
oh,
Yeah.
we have,
Because I saw you use an EKF, and then so if you're using an EKF, it can't be that.
I think EKF, UKF, they were just like two variants of like nonlinear common filter.
Yeah, UKF does a stochastic linearization. EKF does a Taylor series
Yeah.
linearization of the span.
Yeah, exactly. So I think that's why we were pitching UKF, because I think in our initial experience, UKF just tends to give us like a bit better results.
Yeah.
And our measurement function, our sensor models are here. Let me
rephrase it then. So like in a UKF, if you have something like in your estimating poses, you can get the nasty result that if you're facing the wrong way, it'll still give you the same thing, but you'll just kind of get these like weird drifts towards the end. So I was wondering like, are you doing like transformations in like SE2 or SE3, or are you like just kind of stacking out all your sensor stuff into a matrix and just treating it as a linear system? And sorry if it's a really technical question.
no, I think when we define our state having like XYZ and also orientation velocity. So and we augmented the state following the UKF, and we have this like measurement on the orientation from the DVL onboard autonomy in this work only.
Mhm.
So I
Okay, so
didn't see a reason that it would be like having this
Gotcha. So you're just transforming, you're taking your estimates and transforming it to match what the other is. And
Oh, yeah, we sync like all the like coordinates from together.
Gotcha. That awesome.
Yeah, that is also another fundamental challenge doing.
I have lost so many nights of sleep because of unscented Kalman filters. And that's
Oh, yeah.
why I was curious about it.
Yeah, I remember spending like 2 weeks just like getting all the transformation correct.
Yeah,
Yeah.
that's
And I have to, a tip here is just like visualize everything you have in ROBs or whatever, and make sure they are correct before you put them in whatever algorithms you design.
when they work awesome. When they don't work, it's miserable. Thank you.
Question on Zoom. Any more discussion? Good job.